one for the pot. While the tea steeps, let me ask you a question. The flow in this tank is a combination of a vortex and a sink. Water enters tangentially here and flows out at the center. The question is, what path does the water take from the inlet to the outlet? Here I have a long-nosed hypodermic with dyed water in it. With this I can trace the flow and see where it goes. Let's try a little at the surface and see what's happening. At this rate, it'll be a long time reaching the drain. Maybe it never will. So much for surface flow. Let's start over. This time we'll try injecting at about half depth. Again, the pattern seems to be one of nearly circular flow. The water going out of the drain must come from the bottom. A small spur holds the tip of the needle about 1/8 of an inch off the bottom. We can see that the dye goes rapidly toward the center, and this seems to be the answer to our question. We've examined the flow here, which behaves differently at different depths. At the surface, the flow is nearly circular, and this situation persists well down into the flow. This nearly circular pattern could be called the primary flow. Near the bottom, however, the situation is different. Here the flow sweeps inward in a steep spiral and down the drain. This departure from the general situation is called secondary flow. Let's see if we can get a little more specific idea of what we mean by primary flow and secondary flow. In order to understand a flow, it's often useful to think of it in two steps. The first step is to approximate the flow by a description which fits the major part of the flow with reasonable accuracy. This first approximation we call primary flow. The second step is a refinement of the first approximation. It is a recognition of the difference between the actual flow and the first approximation. It is this difference that we call secondary flow. I can stir my tea so as to cause a circular motion. Inertia keeps this primary flow going. The tea leaves are a little denser than the liquid and settle slowly toward the bottom. Since they are denser, we might expect centrifugal force to throw them outward and to find them around the perimeter of the bottom of the cup. But look, they collect at the center. The cup has no drain, but still we find evidence of a flow toward the center near the bottom. We've made an experimental model of this flow in order to examine it more closely. This square box has a circular container inside. It has been rotating around its axis for a couple of hours, bringing the liquid inside to a state of uniform rotation. I can stop the rotation, but the liquid, due to its inertia, will continue to rotate at uniform velocity, except near the wall and the bottom, where a boundary layer will build up. As a first approximation, we will assume that all particles travel in circles around the center of the cylinder, making allowance for the fact that the boundary layer moves at a slower rate than the rest of the flow. We will call this first approximation the primary flow. In order to observe this flow better, we have stretched a very fine wire vertically to the bottom of the tank. Hydrogen bubbles electrolyzed from this wire are stripped off by the flow. By pulsing the current, we can create a series of bubble lines. These lines show up very much better if we dim the room lights. From above, it appears that much of the flow does indeed follow a circular path. Near the bottom, however, a portion of the flow appears to go inward. We can now look into the tank at a tangent to the flow past the wire. And incidentally, we can see that the reason for the square box is to eliminate optical distortion. In this tangential view, we see that the simple circular flow occupies the greater part of the depth. The inward flow extends only a short distance from the bottom. This inward flow is a departure from the assumed primary flow and is what we call the secondary flow. And now let's look inward in a radial direction, that is across the streamlines. We see the circular flow as before and the effect of the boundary layer near the bottom. But notice that this boundary layer appears to affect about the same portion of the total flow as did the inward curving secondary flow. If we look at the radial and tangential views side by side and in the same scale, it becomes clear that this secondary flow occurs within the boundary layer. The inward movement in the boundary layer seems to be directly associated with the reduced tangential velocity in the boundary layer. Our simplified model has given us some insight into this particular secondary flow. Is it the reduced tangential velocity in the boundary layer which results in the spirally inward flow? Let us consider a fluid particle moving on a circular streamline. The pressure force on the outside must be larger than the pressure force on the inside in order to result in a net pressure force inward. The pressure gradient, you will recall, is described by Euler's equation, normal to the streamline. Suppose that a particle in this pressure gradient has higher than normal velocity. It will then have to follow a larger radius and be carried outward. If it has a smaller velocity, it will have to follow a smaller radius and be carried inward. In our experiment, the pressure gradient is established by the main circular flow and impressed on the boundary layer below. The slower moving particles in the boundary layer find themselves in just this situation. Same pressure gradient, but lower velocity, and therefore are swept inward. Tea leaves in the bottom of the teacup are carried to the center. Dye in the bottom of the sink vortex sweeps inward. A predictable secondary flow explains each phenomenon. Suppose we invert the sink vortex by taking the water from the top instead of the bottom. I have closed the drain at the bottom and arranged this siphon to withdraw water from just below the surface. And now I will put some dye near the bottom in the boundary layer as before. You ever see a tornado? Here's another piece of apparatus for investigating secondary flow. It is an open channel with a bend in it. The entering flow is about as clean as we could make it. Laminar, uniform velocity, and where we're going to observe it first, that is well clear of the sides and bottom, nearly frictionless. Here's a sheet of bubbles from a vertical wire. We have tried to keep the size of the bubbles uniform and large enough to be seen clearly, yet small enough so that their buoyancy does not spoil their usefulness as fluid markers. Let's see what happens when this flow enters the bend. Here's the radial view. And the top view. And now a tangential view, looking in this way. The streamlines are alike from top to bottom. We can think of this as a primary flow with no secondary flow at all. And we shall use this simple flow as our concept of primary flow in this channel. How about this sheet of bubbles? Although it may appear warped, this sheet is really in one plane, as a top view clearly shows. We might expect the same streamlines as before when we look at it in the bend. Here's the top view. And the tangential view. The streamlines are no longer identical. Thus there is a departure from the primary flow, which we can call secondary flow. How does it come about? Clearly, the entering flow now has a velocity gradient in it. This time, the velocity gradient is not embedded in a boundary layer. In fact, it doesn't matter how the velocity gradient originated. The crux of the matter is that although all fluid particles are moving in the same direction, some are moving more slowly than others, and all are subject to nearly the same pressure forces. When the streamlines are straight, all particles move in the same direction. Where the primary flow streamlines are curved, the pressure forces carry the slower moving particles toward the center of curvature. When the streamlines are curved and there is a velocity gradient normal to the plane of curvature, we may look for a secondary flow. Here's an extreme case. This time, the velocity gradient occupies the entire flow. So it's not surprising to find secondary flow everywhere in the bend. In a situation like this, it is often easier to explain what's going on in terms of vorticity, rather than trying to identify a main flow from which a pressure field could arise. You will remember that vorticity is twice the average rate of rotation of a fluid particle. If we look for vorticity in the straight channel, we see no evidence of it in the streamwise direction. And in the top view, we see no evidence of vertical vorticity. But if we look horizontally across the flow, we see that there is vorticity, and it is horizontal and normal to the streamlines. In this case, the vorticity is nearly uniform throughout the flow. We can represent the axis of this vorticity by a fluid line which can be observed from above. We can call this line a vortex line. Helmholtz has pointed out that in a frictionless flow, a fluid line coincident with the vortex line will remain so. That is, the vortex lines are transported by the fluid. Let us assume that our flows are essentially frictionless. Thus, here in the straight flow, one arm of the fluid cross coincides with a streamline, the other with a vortex line. As the flow enters the bend, the streamline leg of the cross begins to turn clockwise. Since the vertical component of vorticity is zero, the other leg must begin to rotate counterclockwise at the same rate. But this other leg represents the vorticity in the flow. This means that as the flow goes around the bend, a component of vorticity appears in the streamwise direction. This component increases as the fluid traverses the turn. In the straight channel, the vorticity represented by this fluid line, you remember, appeared in the horizontal view as a counterclockwise rotation of the fluid. We can watch a vortex line enter the bend and observe the same counterclockwise rotation of the fluid showing up as streamwise vorticity. By looking at the vorticity, it becomes clear why the secondary flow sweeps outward at the top and inward at the bottom in this fashion. Let us look again at the notched flow. As before, the only vorticity present in the straight channel is normal to the streamlines and in a horizontal direction. With a vorticity probe, we can investigate this flow. Since the horizontal leg of the fluid cross does not rotate, we can concentrate all vertical legs of all the crosses. The plane swept out by the rotation of this composite vertical leg is perpendicular to the local vorticity. From above, we see an edge-on view of this plane. Now let's look at the bend. Is the plane swept out by the bubbles from the vertical wire still perpendicular to a typical vortex line created upstream? It is indeed, showing that the vorticity was transported by the fluid and was truly marked by the horizontal bubble lines coming from upstream. We must be careful, however, to make our observations reasonably close to the vertical wire so that they are truly a measure of conditions near this point. Thus, in a frictionless flow, an understanding of the secondary flow in a bend can be obtained from a knowledge of the upstream flow. We can now remove the device which produced a special velocity gradient. And use the channel as a simplified model of a river bend. What flow pattern can we expect? The velocity gradient indicates the presence of vorticity perpendicular to the streamlines in a boundary layer at the bottom. In the bend, the radial view fairly closely resembles what we saw in the teacup model. The tangential view also looks very similar. Let us examine this fluid line carefully and see if we can relate this boundary layer phenomenon to behavior we observed before. The straight portion of the line leading away from the wire is close to the bottom wall. Here, local friction is very important, and we can no longer assume that all the vorticity has come from upstream. It is not surprising to find that the plane swept out by this portion of the vertical bubble line is far from perpendicular to the vortex lines created upstream. The elbow is a transition region, and the portion of the fluid line leading up to the primary flow is in the outer part of the boundary layer. Although all of the boundary layer was created upstream by friction, this outer part behaves in a nearly frictionless manner in the bend. The plane of rotation of this portion of the vertical line is almost at right angles to the vortex line from upstream. We saw this behavior earlier in the notched flow. The transverse vorticity created upstream in the boundary layer has caused streamwise vorticity in the bend. If we look a little further downstream in the bend, we see that the vorticity is gathering into what is called a passage vortex. Here the flow is not so simple. Secondary flows are frequently very complex and difficult to interpret, and their causes are often obscure. In this channel, for instance, unwanted secondary flows appeared, which were finally traced to the frictional effect of a dirt film on the surface of the water. It has been useful to use a carefully cleaned up laminar flow in order to observe these simple secondary flows in detail. But flows in rivers and pipes and ducts are rarely simple or laminar. If we were to make this flow turbulent, it would be harder to observe, but the same general flow patterns would occur. Secondary flow in a curved channel acts to displace the normally slow-moving fluid near the walls and replace it with fresh fluid having higher velocity. Thus, it greatly increases the exchange of momentum between the fluid and the walls. This increased momentum exchange explains in part the increased friction experienced in a curved pipe, even when the curvature is sufficiently gentle so that separation does not occur. In this case, the increased friction is explained by the displacement of boundary layer by fresh fluid. Not only is friction in the bend itself increased, but secondary flow persists in the pipe downstream, and for a considerable distance, friction is increased. Material, as well as momentum, may be transported by secondary flow. The meandering of rivers and the ever-changing riverbed is the result of silt carried by the stream, and while the phenomenon is complex, there is no doubt that secondary flow plays a large part. Clearly, there are other classes of flow which can be approached by stepwise approximation, postulating a primary flow and deducing a secondary flow. In fact, the term secondary flow has been used to refer to many different phenomena. We have studied one class of secondary flows, those which result when flow with vorticity has been made to follow a curved path. Here is a more complicated example of secondary flow. When the shear layer on the bottom meets an obstruction, say a bridge pier standing in a river, a horseshoe vortex is formed around the obstruction. The resulting shear stress on the bottom can undermine bridge piers by scouring. This is to be expected since the shear stress directly under the vortex is an order of magnitude larger than normal. And what is even more surprising, it is in the opposite direction.